Ok, bonjour. Merci d'être venu. Welcome. Thank you for coming. So this week we will introduce the one-body, the Green's function for the general case for interacting, even for interacting systems. We'll show how it reduces to what we've seen for the one-body Green's function. And so we have to go through second quantization because even for non-interacting particles, this is useful. So last time we have introduced creation and annihilation operators. Annihilation operators obey the same algebra here, same anti-commutator. For bosons, it will be commutators. And we saw that this allows us to define the number operator. The number operator is very useful. Today, it will really be allow us to write one and two body operators in the using this operator. Sorry, I saw something on the screen and it distracted me. Okay, so you see that if I take the adjoint of this, then I will get that n alpha I times the destruction operator alpha j commutator is equal to minus a alpha j delta ij. Okay, because if I take the adjoint of this, the operators switch. So I put them back in the same order, and all that changed is a minus sign. So are there any questions? Okay, the other trick that's behind writing the one and two body operators in a simple way is this change of basis. So let's see how we change basis. So we said we were working with some one body basis alpha I. So where I equals 1, 2, 3 are the different elements of that basis. So alpha could be position, for example, or momentum, or some orbital. It's quite general. So let's see if we have some other basis. So for example, some basis mu, where the elements are labeled the m equals 1, 2, 3, etc. So we have to use the closure relation for the basis alpha I. Alpha I mu m, okay? So now we saw that the creation operator puts a particle in a state and anti-symmetrizes with the rest of the particles. So if I define an operator C dagger mu m that creates a particle in state m and anti-symmetrizes, it will be equal to sum over I of C dagger alpha I mu m. Okay, very simple. Now if we look at the anti-commutator of this object, we will, oops, this is A, right? A alpha I, this is what we were using here. So if we compute the anti-commutator of this, we will see that if this is a unitary transformation, then this also obeys the same so-called canonical anti-commutation relation. So let's write the anti-commutator of C dagger of C mu m with the C dagger mu n, and use this use this transformation. So it means that for the destruction operator, I have to take the adjoint of this. So it means I will have sum over I j of mu m alpha I. Then I will have the anti-commutator of A alpha I, A dagger alpha j. And then I have this C dagger mu n. I have this relation here. So that's where the A dagger came. And I have alpha j mu m. That should fit there, right? Is it okay? So now this we saw is delta. This is delta ij. So this means that this becomes equal to sum over I of mu m alpha I mn, sorry. Is it okay? I just use the this anti-commutator. So this means that this is equal to mu m mu n. And if that's also an orthonormal basis, this is delta m n. Okay? So that's a canonical transformation. We go from one orthonormal basis to another one. And yeah, that's it. This is u times u dagger, and it's equal to delta mn. Okay? Now there's one thing that is clear here. It's that this notation is redundant in the sense that here I had defined this as creation operator, so perhaps I should have written this as A mu m, right? Like creating in a state mu m. So I can shorten the notation by indeed sort of forgetting, putting the basis in the symbol that is here. So I could have C dagger M and A I, right? And here here I can leave this if I want. You see what I mean? So that is what is done in practice. So for example, if you have some electron in a conduction band, sometimes, so we call the C dagger in state K, and then you have some electrons in F electrons, and then we write them, we write F dagger on site I, for example. But these are also anti-commute. I mean, it's just a way of reminding ourselves what the basis is. So the basis that we will use, so the next week is we start the Coulomb gas, which is sort of the canonical standard example of the many-body problem. So so we will use this basis. So in this basis, we have the destruction operator of a particle at position R. So it anti-commutes with the destruction, anti-commutes with the creation operator of a particle at position R. And if we have if we use the continuum notation, then that's delta R minus R prime. I don't put the vectors because it's just to shorten the notation. And we will work in a sort of mixed basis where we will use a discrete wave vectors. So the wave vectors will be defined on the Brillouin zone, and we can take the continuum limit, as you will see. But for some reason, we prefer to work with this. Equals delta of k prime. So let me show you how this basis works. And while I'm erasing, note here that the operator is this. This is just a position. It's just a label. Okay. So you can, in a field theory, you can think that this is a field and that's defined on the position. So this is not a position operator. This creates a particle at position R prime, but the operator is there. And already in this notation, you see why we call that second quantization. It looks, another reason, it looks as if it's the wave function that's quantized now. R is just a label for the position. It's not an operator. Similarly, here K is not a momentum. K is the label for a wave vector. Okay? You have to keep this distinction in mind. It's confusing at the beginning, but it's very important to know the difference. Now let's see why, what sort of basis gives this crazy behavior. So if we if we write the identity like this, sum over k of k equals 1, then you see that if we multiply here by k prime and use that k prime is delta of k prime, you see that this is equal to k prime, right? If we use this. So when we sum over k, there's delta k prime. So indeed, this guy is equal to 1. That's the closure relation. Okay. Now, let's look to with the psi dagger. So then the closure relation is that integral d cube r of r is equal to 1. To show this, let us multiply by r prime. And then you see that if I have the r prime equals delta of r minus r prime, then when I put this here, I can do the integral, and this is equal to r prime. Okay? So it means that this guy here is equal to equal to 1, like this. The 1 lives in Hilbert space. It's a big one. Really identity. So how do I achieve this? Well, I achieve this by taking momentum eigenstate projected on position r. So the wave function is e to the I k dot r. I put the vectors now for some reason, divided by square root of volume. Okay, so it's a plane wave that's normalized to 1 in a box of volume V. Okay, so to see how this works out, let's look at, what should we look at? Let's look at R prime, for example. And then I put this identity here. So I have sum over K. And this is R K, K, R prime. And now if I use this, you see that I get e to the I k dot r minus r prime. And 1 over square root of volume twice is square is 1 over square, 1 over volume. Now you know that if I take the limit where the volume goes to infinity, that's precisely the way to go from a discrete basis to the momentum basis. If you label, I mean, if the spacing between states is 2 pi over L, where L is if you're looking in the X direction, this is Lx. Then because of this 2 pi here, when you go to the infinite volume limit, this becomes integral d cube k over 2 pi cube e to the I k dot r minus r prime, and that's equal to delta of r minus r prime. Okay, and now if we look at to see that this is consistent, if I look at k prime now, okay, so where am I going to do this? I don't have space, so I will erase it. So k prime is equal to, I use this identity here. So it's equal to the integral d cube r. And then I have again r, and then I put k prime. K prime. And okay, and now again I can use this. So here it's e to the I k prime dot R. And here it's e to the I minus I k dot R. So overall, I have e to the I k prime minus k dot R divided by volume. So this is 0 when k is different from k prime because of periodicity on the and this delta k is 2 pi over L. And when k prime is equal to k, then the integral over R gives the volume, which simplifies here. So that's delta of k prime. Okay, so that all fits together. You can always ask questions as usual. Okay, so we saw that this is, you should normalize these anti-commutation relation with whatever basis you use. So it means we have to use this. Okay, let's move now to one-body operators. So what we have done up to now is to write the states in terms of creation and annihilation operators. But we want to take advantage of this formalism to write operators in that same basis. Because we saw it's easy to, to work with these operators. Basically, you always use the destruction operator to go to the vacuum and get 0. So any expectation you can compute that way. Oh, I forgot some important thing. I forgot to talk about the wave function. So if I have a single particle, I have some state. I have some state phi. And if I project it on the position, this is the definition of the one particle wave function. Now in second quantization, what is this? In second quantization, I have the vacuum. I create a particle at position R in the vacuum, and I take the expectation with respect to phi. Okay? So, and now phi itself, I can write like this. Phi itself, I can write that this is, I'm creating a particle in state phi, acting on the vacuum. Okay? So what is the generalization of this to many particles? The generalization is this. So the wave function will be R1 up to Rn acting on some many-body state phi. And what is phi in general? Phi in general is sum over alpha 1 up to alpha n, if I have n particles, of some coefficient. Let me write this as I alpha I, alpha j, etc. Okay, because remember that I is the one body state. So it's I have the basis. I have several elements, and they're labeled by I. Okay, so I will have n alphas here, but they can take value 1, 2, 3, etc. So I have. Okay, I can make this a little bit shorter here by just writing ij. I, j, etc. And then here I have ci, j, etc. And here I have a dagger alpha I, a dagger alpha j, etc. acting on the vacuum. Okay, so the general wave function is a linear combination of many particle states like this. So the coefficients here are complex numbers. Okay, so in other words, I can have particles in state 1, 2, 3, 4, and then I can create a particle hole pair. For example, I can remove a particle in state 1 and put one in state n plus 1, for example. Then I would have a dagger of alpha n plus 1, etc. acting on 0. You understand? So the complete Hilbert space has to be a linear combination of these so-called one particle states. They're not one particle states, but they are, if you want, independent particle states. So, for example, if you have, we will see that if you have just a Hamiltonian with one body operators, then you can write eigenstates in this way. But in general, it will be a linear combination. So that's important to keep in mind. So the full wave function is complicated. Let's work on just one of these terms. So let's work on one of these terms. So I will, let's work on a dagger of phi 1, a dagger of phi m acting on 0. Okay, so so instead of alpha here, I wrote phi, just by analogy with this. Okay. Now, what is R1 to Rn? R1 to Rn has to be an antisymmetric state. So it means I have to act on the vacuum, 0, and I have to create particles in state psi dagger, psi, I'm sorry, because creating a particle on the vacuum when it is there, I have to use the adjoint. So psi of Rn until psi of R2, psi of R1. Remember that we need to, when we write alpha 1, alpha 2, what do we mean? We mean that we started from the state alpha 1, alpha 2, and we took the dual. So this is 0, psi alpha 2, psi alpha 1, because when we take the adjoint of these operators, they have to be in the reverse order. So sorry for all these notation things, but they're pretty standard. So when you write alpha 1, alpha 2 here, the operators are in the reverse order here. Okay? It's just notation and it's rather standard. So okay. So how can we evaluate this? Well, to evaluate this, we use our change of basis. We write that psi at position R1 is equal to sum over I of A of phi I, okay? And here we want R1 phi I. Sorry, you probably don't see anything now. All my pen are dying on me. Just a second. I took new pens this morning and somehow it doesn't work. Is it okay? It's just a change of basis. And so another way to write this is sum over I phi I star of no, not star, it's the right wave function. Phi I of R. A of phi I. Okay. So now what we do is that we just substitute for each of the psi's here, we substitute this, okay? Now, when will we get something that's different from zero? We will get something different from zero only when all the labels that appear here, all the phi 1 to phi n, when they are the same here. Okay, because suppose that here one of the labels that appeared here is not in this. Then what happens is that I can anti-commute the destruction operator to 0 and get 0. So this, so the labels here, they have to, the only terms that will survive are those where the label is the same. But now they don't need to be in the same order. Okay, as long as the labels here are the same as the labels there, I get non-zero. So there will be many terms, you know, all those that correspond to permutation of this. So let's take this simple case where I have A of phi 1 here and A dagger of phi 1 here. So what will I do? I will use the anti-commutation relation. I will replace this by 1 minus A dagger of phi 1, A of phi 1. And this label cannot appear there because of the Pauli principle. So that now this A can go and kill the vacuum. Okay. So if they are in the same order here, I can just repeat this all the time and I get, what do I get? I get the product of the phi's. Okay, with in this order, 1 up to n. Now, if they are not in this, if it's this one that contains phi 1, then I need to anti-commute and repeat the same thing. So I will get a minus sign every time I have an odd permutation. So what we have shown now is that this guy here is equal to the determinant of phi 1 of R1, phi 1 of R2, up to phi 1 again, sorry. Phi 1 of Rn. And here I have phi 2 of R1, phi 2 of R2, etc. Phi 2 of Rn. And I have phi n of R1 up to phi n of Rn. So that's called a Slater determinant. Okay. So that's just the wave function. Imagine now that you want to compute expectation values of this wave function. Okay. So you have a wave function, you have an operator, and you have this wave function again. So it becomes quite complicated, right? So that's where you say, oh my God, I'm so happy we invented second quantization. Because you'll see how easy it is with second quantization. Okay? So if you do electronic structure calculation, for example, then you work in a basis of Slater determinants. And yeah. So obviously the formalisms are equivalent. So the simple results I will find with second quantization can be found with these determinants. It's not, I mean, there's no magic. The formalisms are completely equivalent. It's just that to establish what I'm going to show trivially with the second quantization is very complicated if you work with these determinants. You need to watch out signs, and you need to prove some theorems. And if you want to compute one body, two body, three body quantities, every time you need to think about it. In second quantization, it's very very straightforward. So let's start with one-body operators. So with one-body operators, let's say we have three particles, okay? So to be specific, if you want, I can work with, I can take as an example the potential, okay? So in first quantization, you have the potential at position R1, and R1 is an operator now. In first quantization, plus V of R2 plus V of R3, and the state here is that it acts on. So again, first quantization, we can take, for example, position eigenstates, okay? And let's not anti-symmetrize for now. We write R prime, R double prime. We have not anti-symmetrized. So when this acts on this state, then it gives V of R plus V of R prime plus V of R double prime, right? because this acts on this acts on that, and this acts on that. And these are position eigenstates. This is the operator, position eigenstate, so that gives this times the state. R prime, R double prime, okay? Now suppose I anti-symmetrize this. So if I anti-symmetrize this, some of this, some of the combinations I will get, for example, R prime, R, and R double prime, and there will be a minus sign here. But when I act with this on that, it will give me exactly the same here. Okay? So it doesn't matter if the state here is symmetrized or anti-symmetrized. So let's do this now in second quantization. So to do this in the second quantization, what we will do then is just to say that if we are in a diagonal basis, so in general, I write U, let's say the diagonal basis acting on alpha I, alpha I is an eigenstate of this, so it's U of alpha I times alpha I. So an example of this was this that I wrote right there. So
just before we continue, the argument we just made for the above expression that it'll be the same, it's supposed that the potential is independent on R1 and R2, for example. It's
a one-body, yes. I
okay.
mean, we will go there to two-body operators.
Okay.
Okay. So for now, it depends only on one label. So you see that what I can do then now is write that U acting on a state alpha I is just equal to sum over I equals 1 to infinity. There's an infinite number of, if the basis is infinite here, of U of alpha I times the operator N alpha I acting on alpha I. And now here I can go beyond just the one particle. I can do like here and put any many particle state. Okay, so that was an example of this big phi here. Big phi. You see that it works out, okay? Now, instead of in the first quantization, if I have n particles, I have to sum R1, R2, R3 up to Rn. Okay, if I have n particles. Here it's different. I sum over all the bases. So the operator does not depend if I have 1, 2, 3 particles. The operator can work for any number of particles. So if there are 3 particles here, like this, then it will just count how many particles are in the eigenstate alpha I. Okay, that was, so here alpha I was the same as the position. Does that make sense? So for example, what is what is the operator potential energy in the second quantization? So this operator here is just the integral d cubed r times v of r times the psi dagger of r psi of r. Okay. So if you want, this is the number operator here. This is the analog of this, and this is v of r. So when it acts on a state, it will count how many particles are at position r, and it will give me every time, v every time there's a particle at position r. So it just looks like the expectation value in Schrodinger's picture. Schrodinger's, when we work with wave functions. And again, you see second quantization, I mean, it looks like it's the wave function. And now if we go to the kinetic energy operator will be integral d cubed r of psi dagger r of minus h bar square. Sorry, h bar is no longer equal to 1 now, just for demonstration. Whoops. Laplacian that acts on psi of r. Okay, so it looks again like the expectation value in first quantization. So to prove this, if you want, you can use the momentum eigenbasis, where p is just the eigenvalue, and then by using the basis we mentioned at the beginning, you can replace p by Laplacian and work it out. But I mean, this is how it comes out. Now, suppose that we are not, that this basis here, this thing is written in some other basis. That's not the eigenbasis. So what would the operator look like? Well, first of all, okay. We just use our change of basis formula. And if you want, we write when n of alpha I is a dagger of alpha I, a of alpha I, we can write this as sum over m n of c dagger m m alpha I, and then alpha j n times the Cn. Okay. And then when I substitute this here, forget the state, just think about the operator. You see that the u of alpha I here is what? u of alpha I is just alpha I u alpha I, where now this is in first quantization. These are just states in first quantization. So that's the matrix element. That's, if you want, that's that's this thing there. So when I substitute for n, when I substitute this here, what will happen, you see, what will happen is that the when I well, here it was alpha I was the same. I don't know why suddenly it became J. There was a transmutation. Okay, so when I substitute this here, what will happen is that I will change basis for the U. So what will be left is that U and this new basis will be equal to sum over I J, sum over MM, sorry. Of C dagger M, M, U, N, where these are matrix element computed in first quantization times the Cn. So you can do this little exercise there. So if somebody gives me, you know, the Hamiltonian, for example, in this form, to find eigenvalues, I still need to diagonalize this object to go back to this form here. And then the number operator acting on the state will just give me the number of particles in that state. And the problem will be diagonalized. Okay, so we're not saving anything. We still need to diagonalize things, except that it's very easy to compute expectation values. Okay, so and so the expression for these operators does not depend on the number of particles, and they're easy to evaluate. So if you understand this very carefully, next time I will take a few microseconds to do the two-body operator. Okay, you will see it's very simple once you understand going to this eigenbasis. Okay, so here like Olivier was asking, if we have R1 minus R2, R2 minus R3, then we need to count particles in in 1 and particles in 2. Okay, so there will be two number operators. There will be n dagger alpha I and n alpha I and alpha j. Okay, so I will let you look at this, and so next time we will play a little bit with this formalism to see, for example, how these operators evolve in time in the case where the Hamiltonian is just diagonal in, for example, in the momentum basis, and that will give us the start afterwards to write down the Green's function. Okay. Okay. Thank you. So see you on Wednesday. And I'm staying if you have questions.
Merci, bonne journée.